Just a reminder, there are three ways that an atom can begin to decay, or three forms of radiation. So there is alpha, there is beta, and there is gamma. And alpha is actually just a helium nucleus. So it equals 2 protons and 2 neutrons. And it's a fairly massive particle in that it carries a lot of mass, but it's not very penetrating. The second option is beta decay, and basically that's an electron. So this has a charge of 2 positive. An electron has a charge of 1 negative. And gamma, which is like a wave of energy. So it's not a particle, the first two are particles, and gamma is a wave. We'll talk a bit more about beta decay when we look at some examples. But the first type of radiation or radioactive decay we're going to look at is alpha decay. So that's this one. Okay, so it's like losing a chunk of helium. Okay, so the way we think about decay is we are given a situation and we need to usually represent it as an equation, or like a chemical formula almost. And how you go about solving these problems is based on that understanding of alpha, beta, and gamma, and basically just adding up the top and the bottom rows and making sure they're balanced. So if we look at an example, if we look at how to do it, okay, so the first example we'll look at is polonium. And for this situation, we're saying polonium-214 emits an alpha particle. So the first thing that we do is we write polonium, or the mother, the original situation, we write that on the left-hand side, and then we write the daughters, or the result of the decay, on the right-hand side. So all we know so far is that we have polonium-214 and that it's going to emit an alpha particle. So we can write it like this. We could either write it like this, helium-42, or we can write it like this, alpha-42. Both are correct. So I'll write both at the same time. So it's the same situation. I'm just saying this is alpha on this side, and this it also could be represented as helium. Now, why I've written 42 is because it's got 2 protons and 2 neutrons. So it has an atomic mass of 4 and a proton count of 2. So then we have to go to the periodic table and figure out how many protons are in polonium-214. Okay, so if we look at the periodic table, we can see that polonium has, and we can write it underneath here like this. I'll write it both ways. A proton count of 84. We can write it down here, 84 too. That's okay. Either way is fine. I'll just draw a line. Okay, so polonium-214 has a proton count of 84. Now what we need to figure out is, if this is the mother, what is the daughter going to look like when there's alpha decay? So basically we just need to make sure this whole row adds up and this whole row adds up. What I mean by that is which element is going to fill in this gap in here. So if we have 214 atomic mass count here and 4 here, well, we have to conserve mass. So this is going to actually equal 210. And then also the bottom situation the bottom line also has to conserve mass. So it's going to be 82. So we can see all of the things highlighted in pink add up from one side of the equation to the other. So 82 plus 2 equals 84. And you could do the same. We could do the same over here. So we've got 4 plus 210 equals 214. Now the last thing that we need to do, so we can write it again down here. The last thing we need to do is figure out which element has 82 protons in it, and that is lead. Just looking at the periodic table. Okay, so it's this number down here that really is going to give you the element, because don't forget this number here could be an isotope of that element. So we really want to look at this, the proton count, to give us the element on the periodic table. And so we could say that polonium will decay to lead, 210, plus emitting when it emits an alpha particle. All right, let's do another example. We have uranium, and it's 232, and it's going to emit an alpha particle. So let's draw it as alpha, 42. And uranium has a proton count of 92. So what is it going to decay into? So first of all, we look at the top line, and we can see this is the sum total on the left-hand side, so we want the same sum total on the right-hand side. So it's going to be 228, and on the bottom, 90 is going to be our proton count, and that is T8. Okay, so we have balanced here and here. Okay, so that's alpha decay. Let's look at another example with alpha decay where you don't know what the mother is, but you know what the two daughter products are. So in this situation, we have an unknown mother or an unknown particle, and in this case, it's going to decay by an alpha particle to form another alpha particle. So let's write it out. So we're not sure what it is, we can write it X decays to form, and we can write it any way here, remember. I'm writing it in different ways on purpose. An alpha particle plus another alpha particle. So what is the original product? What is this mother going to be? So we just work backwards basically. So we can say, again, thinking about this plus this has to equal the atomic mass of the mother, and the proton count or mass has to be conserved. So if we work backwards, so we're going to have an 8 total over here and a 4 total over here, and we're going to get one alpha particle plus another alpha particle. So what is our original product? Beryllium. With a proton count of 4, and it's beryllium 48, and it's going to decay by an alpha. So beryllium 48 is going to give us 2 alpha particles if it decays by alpha, and that's how you work backwards to find the mother.